You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Platform diversity and multi-cloud architecture describes strategies where organizations deliberately use multiple cloud providers or heterogeneous technology platforms instead of consolidating on a single vendor. The goal is to spread risk, improve flexibility, and align technical choices with business priorities. For example, a company may host its customer-facing applications on Amazon Web Services while running analytics workloads on Google Cloud and disaster recovery on Microsoft Azure. This approach avoids dependence on a single ecosystem and takes advantage of unique capabilities offered by each provider. However, it introduces complexity that requires careful planning and governance to manage effectively. Business drivers for multi-cloud strategies vary, but they often include resilience, regulatory fit, cost optimization, and vendor diversification. Resilience improves by ensuring workloads can continue if one provider suffers an outage. Regulatory requirements may demand that certain types of data remain within specific jurisdictions, which one provider alone cannot always satisfy. Cost optimization motivates organizations to compare pricing models across clouds, selecting the most economical option for each workload. Vendor diversification reduces the risk of lock-in, giving organizations negotiating leverage and flexibility. Together, these drivers make multi-cloud an attractive yet demanding choice. Portability concerns present some of the toughest challenges in multi-cloud environments. Moving workloads or data between providers often involves data egress fees, incompatible APIs, and differences in service features. For example, one provider's managed database may use proprietary features that do not exist in another, complicating migration. Even when providers offer similar services, implementation details can vary, making portability more theoretical than practical. To address this, organizations often design around portable primitives, such as containers, and open-source frameworks, though this can mean sacrificing advanced vendor-specific features. The shared responsibility model, a central concept in cloud security, takes on new nuances in multi-cloud environments. Each provider defines slightly different boundaries between what the provider secures and what the customer must manage. For instance, while all providers secure their physical infrastructure, responsibilities around patching, logging, or encryption key management may differ. An organization must clearly understand these boundaries across every provider in use. Overlooking subtle differences can create security gaps, leaving one cloud less protected than another, simply because assumptions were not harmonized. Identity and access management become more complex when spanning multiple clouds. Each provider has its own native identity system, role definitions, and policies, which can create inconsistency and administrative burden. Without centralized identity federation or single sign-on, users may juggle multiple accounts and credentials, increasing risk. For example, a developer may have elevated privileges in one cloud but limited access in another, leading to confusion or accidental misconfigurations. Centralized identity strategies help enforce consistent security, but implementing them across multiple platforms requires careful integration and planning. Networking topologies in multi-cloud environments introduce further challenges. Organizations may connect clouds using VPNs, dedicated circuits like AWS Direct Connect or Azure ExpressRoute, or more advanced transit hubs and mesh connectivity models. Each option has implications for performance, cost, and security. For example, connecting two clouds via VPN may suffice for light workloads, but high-throughput replication between regions often requires direct connections. Mesh topologies provide redundancy but increase complexity. Designing networks for multi-cloud requires balancing performance with resilience, while also ensuring consistent security controls across providers. Data replication and consistency are critical, but difficult to achieve across multiple providers and regions. Synchronous replication may not be feasible due to latency between geographically distant clouds, while asynchronous methods risk losing recent updates during failover. For example, and applications spanning two clouds must reconcile data between them to prevent mismatches or stale states. Solutions may involve distributed databases or middleware layers, but these add overhead. Organizations must weigh trade-offs between consistency, latency, and cost to ensure reliable replication strategies. Configuration and policy drift pose major risks in multi-cloud environments. When each provider is managed separately, configurations can diverge, leaving some systems less secure or compliant. For example, encryption may be enforced on storage in one cloud, but inadvertently disabled in another. Policy drift increases attack surfaces and complicates audits. Automation tools and infrastructure as code approaches help enforce consistency, but only if applied rigorously. Without discipline, multi-cloud can devolve into a patchwork of inconsistent settings that undermine resilience and security. Monitoring and observability grow more complex when telemetry comes from multiple, diverse sources. Each provider offers native logging and monitoring, but combining these into a coherent picture requires aggregation and normalization. For example, latency metrics from one provider may use different formats than another, making correlation difficult. Without unified observability, organizations risk missing incidents that span providers. Solutions include centralized monitoring platforms or open telemetry standards, but implementation requires careful planning. Observability is essential for troubleshooting, performance optimization, and security response in multi-cloud environments. Centralized governance and common guardrails are crucial to keeping multi-cloud manageable. Governance ensures that policies, such as encryption standards, access controls, and compliance requirements, are enforced consistently across platforms. Without common guardrails, teams may implement their own approaches, leading to fragmentation. For example, one business unit might spin up workloads in Google Cloud without aligning with corporate encryption requirements used in AWS. Centralized governance aligns technology decisions with enterprise standards, ensuring that diversity does not devolve into chaos. Cost management in multi-cloud environments requires strict practices, such as tagging, budgeting, and monitoring. Without them, expenses can spiral across providers, making it difficult to attribute costs to departments or projects. Tagging resources with identifiers like project or environment enables financial visibility. For example, a marketing campaign running workloads across two providers must be tagged consistently so costs can be tracked. Centralized tools or FinOps practices help organizations manage costs proactively, preventing waste and supporting informed decision-making across clouds. Ultimately, multi-cloud architecture requires disciplined design, automation, and governance to succeed. While the approach offers resilience, regulatory fit, and cost optimization, it also introduces significant complexity. Without strong architectural principles and consistent automation, multi-cloud can create fragmentation, inefficiency, and hidden risks. Organizations that invest in governance, identity integration, and monitoring frameworks reap the benefits of flexibility and resilience. Those that treat multi-cloud as a quick fix often encounter operational chaos. Success comes from deliberate strategy and ongoing discipline, not from diversity alone. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Infrastructure as Code, IAC, and Policy as Code, PAC, are powerful tools for ensuring consistent provisioning and security across multiple clouds. IAC enables teams to define infrastructure in version-controlled templates, ensuring environments are reproducible whether deployed in AWS, Azure, or Google Cloud. Policy as Code applies the same idea to compliance rules, allowing guardrails such as all storage buckets must be encrypted to be automatically enforced across providers. For example, Terraform scripts combined with Open Policy Agent can enforce consistency in both resource creation and policy enforcement. Together, IAC and POC reduce drift and increase reliability in multi-cloud architectures. Centralized Identity Federation, Single Sign-On (SSO), And conditional access allow organizations to extend consistent identity and access management across diverse providers. By federating identity through a common provider, such as Active Directory or an enterprise identity service, users authenticate once and gain controlled access to resources in multiple clouds. Conditional access adds context, requiring multi-factor authentication when users connect from untrusted networks. For example, a developer logging into AWS and Azure can use the same enterprise account while still being subject to uniform policies. This centralization improves user experience while reducing risk and administrative overhead. Cross-cloud networking patterns must account for security implications of east-west traffic that flows between cloud providers or regions, rather than between a cloud and end users. Connectivity options include VPN tunnels, dedicated interconnects, and cloud exchange hubs. Each approach has different latency, throughput, and cost implications. For example, two providers connected via a VPN may be secure but limited in bandwidth, while dedicated links offer performance at higher expense. Monitoring and securing east-west traffic is critical, as attackers who compromise one environment may attempt to pivot laterally into another if boundaries are weak. Unified logging and trace aggregation provide end-to-end observability across multi-cloud deployments. Each provider generates logs in its own format, but centralized aggregation tools normalize them into a single pane of glass. Traces from distributed applications that span multiple providers can also be stitched together, allowing teams to see how a single transaction moves through the system. For example, a customer purchase may traverse a front-end service in AWS, a payment processor in Azure, and an analytics function in Google Cloud. Without unified logging, correlating events across environments becomes nearly impossible, undermining both troubleshooting and security investigations. Automated compliance scanning, often through Cloud Security Posture Management (CSPM) tools, helps ensure consistent enforcement of security and compliance requirements across platforms. These tools continuously evaluate configurations, flagging misalignments such as open storage buckets or non-compliant encryption settings. For instance, a CSPM platform might detect that an Azure SQL instance is missing encryption, while the same control is properly enforced in AWS. By standardizing compliance monitoring, organizations reduce the risk of drifting away from baseline requirements. Automated enforcement further strengthens resilience by remediating issues in real time. Data egress strategies are vital in multi-cloud environments, where moving data between providers incurs both financial cost and security risk. Large-scale transfers may result in high egress fees, while excessive data movement increases exposure to interception or loss. Organizations often adopt strategies that minimize data movement, such as processing data within the same provider where it resides, or using federated analytics models. For example, instead of exporting datasets from one provider to another, queries may be run remotely with only summarized results transferred. This approach preserves insight while controlling cost and risk. Backup and disaster recovery strategies that span multiple clouds provide resilience against regional or provider-specific outages. A critical database might be backed up in both AWS and Azure, ensuring recovery if one provider experiences disruption. Multi-cloud backups can also mitigate ransomware risks, as attackers must compromise multiple environments to destroy all copies. However, designing cross-cloud backup workflows requires attention to encryption, consistency, and cost. Testing recovery processes across providers ensures that data is not only backed up, but also usable when restored. Vendor-specific services versus portable primitives represent a key trade-off in multi-cloud design. Managed services, such as proprietary AI platforms or databases, offer convenience and deep integration, but may lock organizations into a single vendor. Portable primitives, such as virtual machines, containers, and open-source databases, allow migration across providers, but require more operational overhead. For example, an organization may use Kubernetes clusters as a portable primitive across clouds, sacrificing some advanced vendor-specific features for portability. The choice reflects strategic priorities. Convenience versus flexibility. Training and operational runbooks for cloud-agnostic incident response prepare teams to handle disruptions regardless of platform. Without this preparation, responders may falter when facing an incident in an unfamiliar environment. Training builds familiarity with multiple providers, while runbooks define standardized steps for detection, containment, and recovery. For example, a DDoS attack may be mitigated differently in Azure than in AWS, but a well-designed runbook provides consistent guidance adapted for each platform. This preparation ensures incident response remains efficient and reliable across diverse architectures. Testing and validation cadence for cross-cloud failover ensures resilience is not theoretical. Regular exercises simulate provider outages, testing whether workloads can shift between clouds without service disruption. Canary workloads may be deployed in secondary providers to validate readiness, while tabletop exercises test decision-making processes. For example, an e-commerce site may simulate failing over its checkout service from AWS to Azure, verifying that replication, DNS updates, and authentication work as planned. Without regular validation, multi-cloud recovery plans risk becoming untested assumptions. Governance frameworks provide structure for managing policy exceptions and supplier risks in multi-cloud environments. Exceptions may be necessary when one provider lacks a feature or offers it only in limited regions. Governance ensures these exceptions are documented, risk-assessed, and approved rather than applied ad hoc. Supplier risks are also governed by frameworks that evaluate vendor reliability, regulatory compliance, and financial stability. For example, a framework may mandate periodic reviews of cloud providers, compliance certifications, to ensure continued alignment with enterprise requirements. Governance transforms multi-cloud from opportunistic adoption into disciplined practice. Ultimately, platform diversity delivers benefits only when paired with strong automation, governance, and validation. Automation enforces consistency, governance ensures accountability, and validation proves resilience under real conditions. Without these elements, multi-cloud can devolve into a costly, fragmented ecosystem that undermines security and efficiency. With discipline, however, organizations gain flexibility, resilience, and negotiating power. Multi-cloud is not about collecting providers for their own sake. It is about designing an architecture that balances innovation with reliability, complexity with control, and diversity with governance. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.